Statistics is supposed to give us a handle on any kinds of random influences that occur in situations where we don't want to have randomness, like measurements. I mean, we'd like to have an exact measurement. It's just that that's not in the cards. That's just not how nature works. But we do know that randomness can be predicted, and so for measurements, for example, wherever the randomness is, wherever the random errors are centered around, that is most likely very close to the actual value, and with good equipment, of course, by now a lot of that scatter is not an issue anymore at all. But whenever we have some kind of scatter, we need to start thinking about where our statistical distribution is centered and how far it is spread, and that is what expected values and variances and standard deviations are doing for us. So let's take a look at those things. Basically, the underlying ideas for expected values and variances are the same as for discrete distributions. I'm not sure if we talked that much about the variance anyway, and our introduction to discrete distributions was rather short, so the main analogies really will be about the expected value, which is not that bad. Okay, so the expected value gives us the expected long-term average of measurements, and that is something that the central limit theorem will formally confirm. And the variance is a measure of how spread out the distribution is, and we will see that even if we look at it from scratch. So how do we go from discrete to continuous probability for the expected value? Well, in the discrete expected value, the outcome x contributes a summand x times the probability that our outcome is equal to lowercase x. And that does make sense, because if you've got a high probability to get a certain outcome, say 5, then your expected value ought to be biased towards going to 5, whereas if you've got a low probability of getting an outcome of 1, let's say, then you shouldn't have that much of a tendency to get an average towards 1. In the continuous setting, however, that is problematic, because the probability of every individual outcome for a continuous random variable is 0. And here's again where we're going to use the mantra of calculus, that a little differential step is what we want to use. If we're looking at a density function, and we're looking at the density function at x, well then this is a rectangle with 0 width, so the probability to get exactly x is 0. But if we now look at the rectangle between x and a little differential step dx, well then the probability to be in that interval, well technically it's the integral of the density function over that interval. However, if that interval is really short, then the integral is basically just the area of the rectangle height fx of x dx times width dx, which is as shaded here. And so that means that an integral of a short differential length x to x plus dx should contribute about x times f of x dx, right? The value, which is the value here, times the probability. Don't spread it out all the way. It doesn't want to do that. Times the probability, which is the probability here. Well, yeah, okay. It just doesn't want to split the x off. So an interval should just contribute value times density times a little dx, and that is something then, of course, that we can also turn into a summation, because what we do know, and it's a good bit more than a mantra and can even be justified, even though non-standard analysis takes a while to do all the proofs. Basically, what is a summation in the discrete setting becomes an integral in the continuous setting, because integrals are continuous sums. That is something that physicists will certainly agree with. And so the expected value or mean of a continuous random variable with probability density function f sub x is expected value of x, or also denoted mu sub x. It's the integral from negative infinity to infinity of x times the density dx. And that formula is exactly the same as the formula for the center of mass of a linear mass density of total mass 1. Which was center of mass along the x-axis, because that would be just a linear mass density just sitting along the x-axis. It's the integral from negative infinity to infinity x times density times dx. And so the analogy between probability and mass that people often use, and probability density and mass density, that certainly also persists to the expected value. The expected value in many ways really is the center of mass of our density function. And the central limit theorem will show that the expected value actually gives long-term expected averages of sample values. Okay, now what we have to be careful with is just because this thing is called the expected value doesn't mean that the value itself is very likely. So for example, if you have what people call a bimodal distribution, a bimodal density, well then the center of mass of this thing, if we were to put this on a balance beam, the center of mass would be around here. And so the expected value, if you put a wedge under here, that would be exactly where that thing would balance. But we can already see the probability to get something near the expected value is really, really small, right? So we should not necessarily expect measurements, individual measurements, to give numbers near the expected value. Long-term averages will be near the expected value, and that also makes sense. If I take a bunch of measurements from a distribution like this, I get a bunch of values here, I get a bunch of values here, and the average will be somewhere in the middle. And that also means that maybe something like expected average would be more accurate terminology, but expected value has just become very, very customary. Okay, so now we're just going to compute some expected values, so just do some calculus with these things. So if we're looking at a uniformly distributed random variable, f of x a b being 1 over b minus a for a smaller or equal x smaller or equal b, and 0 otherwise, and the notation here is different from the notation that's been customary so far. Let me fix that real quick. And we're back. Well, if these notational things are the only thing that happens here, then we ought to be doing pretty well. So how do we compute the expected value, which is claimed in this theorem to be a plus b over 2? Well, first of all, for a uniform distribution, it ought to be very sensible that the expected value is in the middle. And if we want to compute it, well, we would compute the expected value of the uniform distribution with parameters a and b. That would be the integral from negative infinity to infinity x times the density function, which of course is just the integral from a to b, because the density is 0 outside that interval, of x times 1 over b minus a, and that's a very simple integral dx to compute, because it's just 1/2 x squared times 1 over b minus a, which is just also written out here, in the bounds b and a, which would be b squared minus a squared over 2b minus a. And as you factor b squared minus a squared into b minus a times b plus a, and cancel the b minus a, you end up with b plus a over 2. No problem. Alright, the visualization then, I like this balance beam thing, right? The uniform distribution's density function is this rectangle here. If you put that on a balance beam, the center of mass ought to be here, and so if at b minus a over 2 you put a wedge underneath, then this ought to be perfectly balanced here. If we're looking at exponentially distributed random variables, well, we know what the density function is, and we claim that the expected value is theta. The proof is a really good exercise for integration by parts, which we are not going to do. That's something that you could do on the homework, for example. But you want to be warned here. Remember that exponential distributions are also often given using the parameter lambda equals 1 over theta. So sometimes the expected value then is stated as 1 over lambda. Be careful as you are reading statistical or other texts that use this distribution that you are adhering to and understanding the conventions that the authors are using. Alright, visualization. Well, we know that the exponential distribution's density is this exponential decay, and so if we put that on the balance beam, it's really hard to say, but basically the center of mass, if we eyeball it, could be somewhere around here, and that would be balanced at theta, basically. Finally, we have experience with standard normal distributed, or with normal distributions, and so let's take a look at normal distributions with standard parameters, with parameters mu and sigma. Here's the density function, we know that thing, and we say, or we claim that the expected value is mu from the picture. That would make sense, right? Because this is a bell curve that is symmetric around mu. How do we compute the integral? Well, the substitution z equals x minus mu over sigma, which we have seen before and which is very beneficial for these things, well, that gives that dz dx is 1 over sigma, and then dx is sigma dz, which means that as we compute the expected value, we first get the integral of x times the density function. We realize that the exponent is just x minus mu over sigma quantity squared divided by 2 with a negative sign, and we copy everything else. And that gives us then that if we go from the back, sigma dz, that's the dx. The x minus mu over sigma is replaced with a z, that's perfectly fine. The factor out here is kept, but then of course the x we have to replace somehow, and the way we do that is that we solve this equation for x, and we realize that x is z sigma plus mu. Alright, now we can break that up into two integrals. Neither of them is terribly pretty, but then we use some of the calculus that we know, some of the geometric stuff. So first of all, clearly, this plus sign is this plus sign here. I just broke the integral up into the integral z sigma times the density plus the integral mu times the density. Well, what I have continually preached is that there is no decent antiderivative for this density function. But let's take a look at the first integral, and we realize that this density is an even function, and multiplying by z makes it an odd function, and the integral of an odd function over a symmetric interval, whether the interval is finite or infinite, integrate an odd function over a symmetric interval, you get 0. So this guy here is 0, which is great. And this one here, well, okay, the mu we can factor out, and the rest, we had gone through some blood, sweat, and tears with numerics to say that it's 1, and in multivariable calculus we can actually prove it completely symbolically that the integral is 1, but basically that means we get mu times 1 from the second integral, so that means the whole thing is 0 plus mu, which is mu as claimed. And the visualization then, of course, is if we're looking at our bell curve, well, if we were to balance that, it would be balanced right in the middle, and the middle is the expected value mu. Alright, if we want to actually take the expected value of a function of our random variable, if we take the values that our random variable spits out and process them some more, well, then the expected value of that can be obtained with a similar integral. You just would take g of x and integrate that product of that thing with the density function. And if you have g and h that are functions and a, b, c that are numbers, then the expected value of a linear combination like that is the expected value of a times g of x plus b times h of x plus c is, well, I can't really simplify the expected value of g of x, but remember that the expected value is an integral, and numbers can be pulled out of an integral, so I can pull the a out. The expected value is an integral, which means the expected value can be moved through sums. That's why things break up. We can pull this number b out just the same, and then finally, the expected value of a constant is always just the constant itself, because any process that keeps giving us the same number, we would expect to give us the same, we would expect us to give that number on average also. Okay, so now let's take a look at how measurements spread, and basically in order to just get an idea of what spread can do is let's consider say a time measurement that we do by hand, say it's a 100-meter race or something like that, and you measure the times of the runners by hand. If you've got a bunch of people with stopwatches, well then some people will trigger the watch too early, some people will trigger the watch too late, and the whole thing will be quite scattered because human reaction time, as magnified here, just has a good bit of spread in it, and overall you'll get a certain average. If you compare that to an electronic measurement, where maybe you have several mechanisms or so, well, you will still have scatter, and the scatter will be very, very small, but it'll be there. In fact, if you're looking at human stopwatch measurements versus electronic measurements, these values would be a lot more clustered, but they would still be different because as the starting shot is fired, which triggers the mechanisms, the triggers themselves may have small electronic delays that would still contribute to some scatter. That scatter will not be significant for the measurement down to the hundredths, which is what you do in a 100-meter race, for example. But nonetheless, the scatter is there. And so basically, the idea for the variance is we somehow want to measure, we want to determine how much something that is influenced by randomness is scattering, because that is then an indicator of the quality of a measurement, for example, or it is an indicator of the reliability of the random process that we're investigating to be near or not so near the average. Okay, so the definition is the variance of a continuous random variable with probability density function f sub x is variance of x being the expected value of x minus the expected value of x quantity squared. And that's something that is then basically the integral of x minus the expected value quantity squared density dx. And well, that deserves a few comments, because figuring out how far we can expect to deviate from the expected value from the purported center of the distribution, that makes sense. It also makes sense that we don't want to count negative signs, because a deviation to the left is without further information just as bad as a deviation to the right. And so then people could rightly say that if that's what we're interested in, just finding the expected value of the absolute value of this stuff would be equally, if not more, sensible, because then taking the absolute value also wouldn't mess with the units. It turns out that squaring this deviation certainly also erases the negative signs, but leads to something that is easier to compute with than the corresponding integral that we could have had if we had taken the absolute value here. And that is something that actually early on in the early days of statistical analysis people were quite worried about, until they realized, look, we want to measure something and we want to have something that can be computed, and because we can build a nice theory around the variance, we just have to bite the bullet there and take that square. And if we ever want to rescale back to the scale on which the outputs of the random variable live, we would just take the standard deviation, which is the square root of the variance. So it's not ideal, but it is the kind of thing that has become very customary for hundreds of years now, and it works. It builds a good theory. What we can then do is, in order to compute variances, and that's what's going to absorb our attention for the rest of this presentation, we can realize that actually the variance is also the expected value of x squared minus the square of the expected value of x. And that's of course something that we want to prove. Well, the variance is the expected value of x minus e of x quantity squared. Well, we can multiply that out, right? That's the expected value of x squared minus 2x e of x plus e of x quantity squared. That's just the binomial formula. And now we're going to use a theorem from the previous panel, which is that we can pull the expected value into sums and differences, and we can take numbers out. So this becomes the expected value of x squared minus 2e of x. Well, that's basically this 2 and this e of x here, right? And what remains is the expected value of x. And then the expected value of a constant is just the constant. And, well, that's now just straight algebra. E of x squared stays. This is 2e of x quantity squared plus e of x squared. So that's e of x squared minus e of x quantity squared. Okay, so now we're going to just go ahead and compute a couple of variances, such as the variance of a uniformly distributed random variable over an interval a, b, and that variance is b minus a squared over 12. Okay, so that's not really something that we can just geometrically predict like the center. That is something that really has to be computed. So let's take a look at it. The variance is the expected value of the square of the random variable minus the expected value of the random variable squared. So that's the integral from negative infinity to infinity of x squared times the density. It doesn't want to highlight here. Well, Okay, x squared times the density, not sure why I did that, minus the expected value squared, which we already had. Well, that's the integral from a to b, x squared 1 over b minus a dx, plus b minus a quantity squared over minus b minus a quantity, minus b plus a quantity squared divided by 4. And, well, the integral of x squared is 1/3 x cubed. We keep the 1 over b minus a. We have to evaluate from, we have to go from a to b. And the minus b plus a quantity squared divided by 4, of course, stays with us from before. Well, then that's just b cubed minus a cubed divided by 3b minus a. And we keep the subtraction of b plus a quantity squared divided by 4. And here, this is one of those where then certain slightly arcane, and some colleagues will probably disagree with me and will say that these are formulas that we have learned and we may have. We have a formula for the difference between two cubes, which is that b cubed minus a cubed is b minus a times b squared plus ab plus a squared. And everything else is copied here, of course, and so with that we can cancel the b minus a. And so we end up with b squared plus ab plus a squared divided by 3 minus b squared plus 2ab plus a squared over 4. And so if we're looking at that, b squared over 3 minus b squared over 4 is b squared over 12. A squared over 3 minus a squared over 4 is a squared over 12. And this one gives us a little bit of a problem, because ab over 3 minus ab over 2, that would be 1/6, which is negative 1/6, which is negative 2/12. And so that would be, we get b squared minus 2ab plus a squared over 12, and that's b minus a quantity squared over 12. I guess here's where my other mantra comes in. You want to be able to do certain things mentally. If that step doesn't work for you mentally, just use paper and pencil, work it out. It'll be exactly what is claimed to be here. And so that means that, of course, the computations have gotten harder. And so if we're looking at the exponential distribution, well, the claim is that the variance is theta squared. And, well, the proof for that is a good exercise in integration by parts. You would integrate x squared times the exponential density and then do all the other subtractions. And so that's another thing that I'll leave you to do. Now, quick word here. The standard deviation, therefore, would be theta, because, right, for the standard deviation, we take the square root of the variance. For the uniform distribution, that's just as well, that just makes things more complicated in that formula then. Finally, we could also, and want to look at a normally distributed random variable with parameters mu and sigma. And the variance is sigma squared, and that explains why sigma is called the standard deviation, because it is the standard deviation of a normal distribution. The computation, actually, the first two we used e of x squared minus e of x quantity squared. Well, we're actually going to compute the variance of the normal distribution with the direct formula, with the definition of the variance. It's one of those situations where whenever you've got two ways to compute something, you always have to choose which one is better, and in this case, actually, the definition is better. So let's remember that the standard substitution for normal random variables is that you set z equals x minus mu over sigma. That gives you dz dx being 1 over sigma, and then dx equals sigma dz by multiplying by dx and multiplying by sigma. And so now your variance, therefore, is set up to be the integral from negative infinity to infinity x minus mu quantity squared times the density function dx. And with our substitution, we realize that our dx becomes sigma dz, and the sigma is already cancelled with the sigma over here. X minus mu squared over sigma squared becomes our z squared. Other than that, we've got the negative 1/2 entity squared over 2 in the exponent. The 1 over root 2 pi stays a 1 over root 2 pi. And x minus mu squared, well, just multiply this equation by sigma, and you realize that x minus mu quantity squared is sigma z quantity squared. Alright, so that is sigma squared times the integral of z times z 1 over root 2 pi e to the negative z squared over 2. And of course, as I keep saying, these integrals are hard, so we need to use a little bit of trickery here. And the trick is that we're going to do integration by parts in exactly this fashion, because we can find an antiderivative of this function, and this one we can differentiate. And so the way this works is, this is sigma squared times quantity. Well, okay, so how does integration by parts go? You keep the one that you want to differentiate, so you keep the z, and when you integrate z times 1 over root 2 pi e to the negative z squared over 2, you end up with negative 1 over root 2 pi e to the negative z squared over 2. That is the antiderivative of this function. You could verify that by quickly taking the derivative, or by doing the requisite u substitution, u equals negative z squared over 2. And well, then of course when we do integration by parts with bounds, that means we have to indicate that this is for z going to minus infinity and for z going to infinity, minus the integral from negative infinity to infinity of, well, now the derivative of this z is 1, and I didn't write that down, and then we have the antiderivative of this thing, which is a negative 1 over root 2 pi e to the negative z squared over 2 dz. And well, now we can trick around some more, because we realize that as z goes to infinity, the exponential decay is much faster than this linear growth, so we get a 0 for the first part. We also, as z goes to minus infinity, this is still exponential decay, right, because we've got z squared, so that also goes to 0, which means this whole term here in the front becomes 0. Another way to work that out would be possibly with L'Hopital's rule. No, I don't think L'Hopital's rule will help. Here we really have to use this idea that exponential decay just beats polynomial growth, or do some kind of a substitution. And well, the other one, minus minus is a plus, right? And the integral from negative infinity to infinity of 1 over root 2 pi e to the negative z squared over 2, we've talked about that before, that's 1. And so that means that the variance is sigma squared, and that ends the problem. So what are we seeing here? We're seeing that computing expected values is another beautiful place for practicing integration, and for also working out integration with parameters, which is kind of nice. This is the kind of thing that prepares you for what happens in further classes, where people will throw parameters around and simply say, well, yeah, okay, you can compute this integral, and we're not going to spend time with this because we have to think about the statistical or the physical or the engineering significance of the process. Whenever that happens, well, that's when something like this prepares you to be cold-blooded, and to make sure that you just say, well, okay, I'm going to use paper and pencil, work out the integral, and then move on, but I'm not going to let the computation distract me from the meaning of it all. Alright, with that, you probably have some really neat integrals assigned on the homework. Have fun with those.